All right, let's jump right into this explainer. Today, we're going to act as the lead architects, and we are building a robust, HIPAA-compliant clinical AI triage agent from the ground up. If you've been tracking the lightning-fast developments in AI recently, you know that designing an agent for healthcare, well, it's not just about picking the smartest language model off the shelf. It's an entirely different beast. It requires incredibly strict architectural discipline, mainly because the consequences of a system failure aren't just, a bad user experience. They directly impact human lives. So right off the bat, we have to establish the stakes here. This quote from our sources perfectly hits the nail on the head. In healthcare, an AI mistake is a patient safety incident. Just think about it for a second. A general consumer AI agent pulls context from a quick web search, right? But a clinical agent retrieves protected health information from EHR databases, deep patient records, and lab results. If a regular chatbot hallucinates a restaurant's opening hours, it's just kind of annoying. But if a clinical AI hallucinates a normal heart rate for a patient who's actually in acute distress, that is quite literally disastrous. This demands a level of rigorous architectural discipline that most standard consumer frameworks just completely ignore. To navigate those high stakes, here is our blueprint for today. First, the clinical AI blueprint. Second, the 4-layer architecture. Third, we'll actually look at building the triage agent. Fourth, essential clinical safety guardrails. And finally, number 5, the implementation path. Let's get into it. Starting off with part 1, the clinical AI blueprint. Before we lay down a single line of code, we have to recognize that a clinical AI is fundamentally different from your standard chatbot because it needs direct, highly secure access to authoritative clinical systems. And honestly, this number right here perfectly illustrates why we're even taking this on. A successful AI triage system can dramatically reduce wait times for critical patients. Research shows that integrating a rule-based AI scoring engine projects a massive 40% reduction in wait times in the emergency department for the most acute patients. We are tackling a very real, very dangerous problem. Manual triage accuracy usually hovers between 78 and 85%, and there's a ton of variability between different nurses and hospitals. Under-triage delays critical, life-saving intervention, while over-triage completely burns through precious hospital resources. Moving on to part 2, the 4-layer architecture. This is the gold standard for production healthcare agents. This architectural foundation is what separates real production systems from those weekend proof-of-concept projects. It's built on 4 mandatory layers. First up is the reasoning core. This decides what thinking happens where. For example, you might use a massive frontier model for high-level planning, but switch to a specialized clinical model just for extracting medical entities. Second is memory. Third are tools, which act as the agent's hands to interact with the outside world, like querying FHIR APIs, which is the industry standard for healthcare data, or handling scheduling. And fourth is orchestration, the actual execution loop. Here's a pro tip. For high-stakes healthcare, pure agent orchestration is actually way too brittle. What you really want is a hybrid workflow, where a deterministic engine sets the safe boundaries and the agent does its reasoning within that rigid skeleton. Now, I see this pitfall all the time, so let's clear it up. You absolutely cannot just dump everything into a single giant vector database and cross your fingers. It will not work. You have to rigorously separate your memory types. Working memory is the agent's temporary scratch pad for a single task, like holding on to intermediate observations while it's evaluating a patient. Episodic memory, on the flip side, is the highly structured past history tied to a specific patient's case. Using vector retrieval for working memory is just way too slow, and when it comes to episodic memory, recency and exact patient identity matter infinitely more than semantic similarity. All right, part 3, building the triage agent and seeing how this looks in the real world. Let's see how all this theory translates directly to the bedside by looking at a real Emergency Severity Index, or ESI, triage application. Its job is to automate patient severity classification. Instead of some chaotic, unstructured chat interface, we use a guided web form as our data collection layer. We're safely capturing multimodal inputs right off the bat. The system collects demographics, vital signs, the patient's AVPU consciousness level, which, by the way, stands for alert, verbal, pain, unresponsive, and 25 specifically curated clinical symptoms, all before the AI reasoning engine ever touches the data. This step is absolutely critical. Structuring the input upfront helps the feature engineering layer normalize the data and apply the proper clinical significance weighting. And honestly, the performance metrics for this approach will blow you away. The AI system achieves a stunning 95% classification accuracy, and it does it 3 times faster than manual processes.
While a manual triage typically takes about 5 to 8 minutes and sits at that 80% accuracy mark, this AI system completely evaluates the patient in under 2 minutes. What does that mean down on the ER floor? It means life-threatening conditions are flagged almost immediately upon data entry. It completely streamlines the flow of the entire emergency department.
What we end up with is a crystal clear result dashboard. Now, this setup doesn't require any complex custom model training, but it provides deterministic, fully auditable outputs that you can deploy immediately. Take an instance where the system flags a patient as ESI level 1, meaning immediate intervention is required. The absolute best part about this approach is that it generates a comprehensive AI reasoning log alongside the decision. It gives you 100% decision transparency, which is something manual human processes simply do not offer. Which brings us to part 4, essential clinical safety guardrails. Listen, you can't just release an autonomous agent into a hospital and hope it behaves itself. It's a massive liability. These 4 security mechanisms have to be baked directly into the architecture from day one. They are not prompt engineering afterthoughts. We need confidence scoring to estimate certainty before any output. We need source citation so the agent explicitly points to the exact lab result or vital sign it used. We need hallucination detection acting as a strict filter to catch claims that aren't actually in the patient's retrieved context. And finally, human review checkpoints to guarantee strict clinical oversight. Take confidence scoring, for example. It acts as a massive safety net. The system calculates this by looking at the ratio of abnormal indicators. Any output that falls below a specific confidence threshold gets explicitly flagged for uncertainty rather than just being presented to the doctor as a clinical fact. If the agent isn't entirely confident, the output gets confidence-gated and routed straight to a human reviewer. This is such a smart design choice because it keeps your human reviewers laser-focused exclusively on the tricky edge cases instead of burning them out reviewing thousands of obvious, high-confidence decisions. And that leads us to human-in-the-loop or HITL workflows. Regulators mandate this. It's not a temporary limitation while the AI gets better. It is a permanent architectural requirement. The ultimate decision must always rest with a human clinician. The EU AI Act, for example, strictly requires this kind of human oversight for high-risk AI systems, like medical devices. The system does the heavy lifting, surfacing options and making suggestions, but the clinician reviews, corrects, or approves it. In fact, research actually shows that while fully automated AI systems might plateau around 80% accuracy, workflows that utilize a proper human-in-the-loop architecture can achieve up to 99.9% accuracy. Teamwork literally makes the dream work. Finally, part 5, the implementation path, your roadmap to production. So, how do we actually go live? Getting from architectural theory to the hospital floor requires a highly calculated roadmap. A secure FHIR integrated clinical agent takes a strict 20-week build path. And I'll tell you right now, skipping that initial data foundation phase is the absolute fastest way to completely derail your project. Weeks 1 through 4 are all about establishing FHIR API access, getting business associate agreements signed with every vendor, and setting up your audit trails. Then, weeks 5 to 12 are where you actually build the core agent, focusing hard on that reasoning loop and hallucination detection. Finally, weeks 13 to 20 are all about validation, compliance, and deployment. You're testing against representative cases and passing brutal security reviews. You simply cannot rush this. Slow is smooth, and smooth is fast. To wrap up this explainer, I want to leave you with a real gut check question to challenge your own readiness. Your AI might be able to reason, but can it pass a HIPAA audit? Look, hooking up a language model that can chat about medical symptoms is the easy part. But building an agent that securely queries a patient's protected health information, cites its sources, flags its own uncertainty, and safely routes its conclusions through an auditable human-in-the-loop workflow, that is the real challenge. If your architecture doesn't start with security and strict memory separation on day one, you aren't building a clinical agent. You're just building a liability. So think about how your current data structures hold up to that standard and what you might need to completely restructure before you write your next line of code.